So welcome everybody. Thanks for being here on site or on the bridge. Today we are going to talk about confidence intervals. So the talk begins by XKCD strip illustrating differences between frequency statistics and Bayesian statistics. So essentially, there are two guys or two women, we don't know, a frequentist statistician and a Bayesian statistician, and they have a device that is able to detect whether the sun has exploded. But there is a source of error, which is the fact that the machine rolls two dice, and if there are two sixes, then the machine lies, and in the other case, it tells the truth. So they try the detector. The detector says, yes, the sun has exploded. And that's where their approaches differ. The frequency statistician says, okay, so if the sun is still here, what is the probability to have this surprising answer, which is that it has disappeared? The probability is 1/36. So it's very surprising. It would be very surprising that the machine says yes, whether the sun is still here. So I conclude that the sun has exploded. I reject the null hypothesis. And the Bayesian statistician answers, okay, do you want to bet $50? Because of course we have a huge prior on the fact that the sun did not explode, and it's much more realistic to think that it hasn't, and just that the two dices come up with the 6. Okay, let's go. So at the beginning, in fact, I wanted to talk about confidence intervals for Monte Carlo methods, and in the particular case of a Bernoulli variable, which is more or less one of the simplest cases. Maybe the simplest case would be with normal distributions. But okay, in fact, even in that very simple case, the question of confidence intervals is quite complicated. And in passing, I wanted to illustrate the problems that there are with confidence intervals, the difference between the frequentist and the Bayesian approach, and so on. And when I was working on this presentation, I saw a very illuminating example that shows what a confidence interval is and isn't. And essentially, I decided to make my whole presentation about it. So you will need to wait maybe a few months to have my true presentation on the Monte Carlo methods. And today it will just be an illustration of the problems with confidence intervals. So sorry for the spoiler, but what I will tell you today, essentially, it's that it's complicated. Generally speaking, you probably know that probabilities are already full of traps. Statistics, which may be seen as a derived branch of probabilities, is even worse in terms of traps, and frequency statistics are even worse. And in particular, if you just take away something from this talk, I would like you to understand that confidence intervals are often not that complicated to compute, but very complicated to interpret. And it's very easy to say wrong things about the interpretation of a confidence interval. In particular, they shouldn't be interpreted as probabilities a posteriori. And if you don't understand what I mean for the moment, I hope that you will understand what I mean at the end of the talk. So to begin with, we are going to do a bit of theory. Then we are going to focus on one example for the rest of the talk, and then I will conclude. So sorry, there is too much text, but we need a bit of formalism. So imagine that you have x, which is a random variable. Typically, x will be constituted of several repeated experiments that are supposed to be independent and identically distributed. and you want to use that data to evaluate the unknown parameters of the distribution. So we will assume that you want to estimate one real parameter that is theta, which could be, for example, the mean of the distribution, the true mean, I mean. And there are also other parameters of the distribution that you can know or not know, such as the standard deviation, for example. And you give yourself a confidence level that will be typically 95% or 99% or 99.9%. A confidence interval for the parameter that you want to estimate, theta, with the confidence level gamma, is a random interval. It's very important that it's a random interval that you deduct from X, and that is such that whatever the true value of theta and phi are, you will have that the probability that the interval contains theta is at least gamma. So, as you probably noticed, I didn't say the probability that theta is in the confidence interval. I said the probability that the confidence intervals contains theta. It's exactly equivalent, but it's interesting to think of it that way because in the frequency interpretation, theta is fixed. You don't know it, but theta exists somewhere, and you simply don't know it. And since theta is fixed, you want your procedure to work for any value of theta because you don't want to be trapped by reality. If the reality happens to be a specific value of theta, you want your procedure to work. And what is random here is the confidence interval, because since the data X is random, it will give you a random interval. Okay, so now just to see that you follow me and that you're not asleep, do you have an idea of a confidence interval that will always work? Sorry?
No,
so
mean max.
The domain.
It's a real parameter,
Yeah.
simply a real parameter. So yeah, minus infinity plus infinity. Thank you. Thank you. So of course, end of the talk, we have the solution to the problem, and we can always give R. But of course, we want to use the data as much as we can. So the goal of the whole procedure, of course, is to reduce the confidence interval. So we want a confidence interval to be small. In a nutshell, the definition of a confidence interval is that whatever the hidden value of theta is, you want the confidence interval to contain theta with a probability that is at least gamma. So in terms of interpretation, before applying the procedure, what do you think you can say? In terms of interpretation, what does it mean? Here again, just to see that you're not asleep. Yes, that's essentially a reformulation, but yeah, that's it. There's already a probability, okay? So when I am going to do the procedure, and I can say that the probability that theta will be in the in confidence interval is at least gamma. So that's the probabilistic interpretation. And in probability, when you have a probabilistic interpretation by the law of large number, you also have a frequentist interpretation, which is that if you repeat the procedure many times, then on the long run, a fraction, at least gamma of the experiments, will lead to a correct result, essentially. Okay, and now after. So now you have drawn your X, you have done the procedure, and in terms of interpretation, what can you say? So you have your confidence interval at 95%, for example. What can you say about the results you have? Which information did you gain?
You would be tempted to say,
you would be tempted to say that you have a probability that the parameter is in the confidence interval, but in fact, there is no probability anymore. Theta is fixed. Now your data is frozen. So either theta is in the confidence interval or it's not in the confidence interval. That's just what you can say. It's not very informative. So what is important in this is that the confidence interval applies to the procedure as a whole and not to the end result of the procedure once it's done. Okay, so now let's look at the Bayesian way with what is called credible region, or you can say also credible interval, but it was convenient for me to have different acronyms, so I preferred the terminology credible region to denote it by CR. So now in the Bayesian interpretation, theta is not fixed, it's not a state of the world. It's something that is random. So you can imagine either that it's really random or that the randomness of theta simply reflects the prior information that you have on theta. You have also other parameters, phi, that can also be random. Once theta and phi take their value, then x will be drawn according to a distribution that itself depends on theta and phi. You give yourself a credibility level, so typically 95%, for example. And then you suppose that the value x is fixed, which is typically the situation in which you are once you have drawn your data, once you have acquired your data. And then a credible region or a credible interval for theta with credibility level gamma is an interval UV such that the posterior probability that theta is in the interval is at least gamma. So I have not written explicitly prior and posterior, but here, of course, is the formula for the posterior probability. And here, it really makes sense to think of the probability that theta is in the credible region, because in the Bayesianism, Bayesian interpretation, in fact, the parameter itself is random. So here again, of course, a very easy solution would be to give R each time. Of course, we also want the credible region to be smaller if we can. And once again, just to see if you are asleep, without even looking at X, would you be able to give a smaller credible interval, credible region? Sometimes.
Depending on your distribution.
Sorry?
Anything that falls on your distribution 95% of the time, regardless of the outcome. So if you know the distribution theta,
yeah, the support of the prior. Yes, the support of the prior would be a credible region anyway, with a credibility 100%. Yes, and sometimes maybe smaller than R. Yes.
U and V do depend on X, right? You didn't write it explicitly like last time. They do. You can choose U and V based on what you observe.
So here, X is fixed.
Yes.
So yes, but what you can, if you want, you can define a procedure that for each X associates U of X and V of X. But in fact, it's not even necessary. You can do the job a posteriori and only for one value of X if you want, which is not possible in for the.
You are doing it based on the value of X.
Yeah.
You cannot define them prior. It's a posterior thing. You cannot define them prior to the observation of X.
Yeah, you can define a procedure like in the frequentist approach, but it's not necessary to check whether the end result is a credible region or not. So here in a nutshell, so with X given the probability that theta falls into the credible region, the posterior probability that it falls into the credible region is at least gamma. And for the interpretation, it is essentially what we have just discussed, that if you accept the prior on theta, and that's a big assumption, then gamma actually is a probability. It's a probability a posteriori. By definition, it is a posterior probability. And unlike the confidence interval, it concerns the end result. So you can say whether one particular interval is a credible region for a particular value of x, whether it makes no sense for the confidence interval, because you have to judge the procedure as a whole in the confidence interval. Of course, in practice, and that is what you mentioned, we generally define the whole procedure because you just want to make the job in advance and to put it in a computer and so on. But on the principle, it is not necessary. And the price of all this, because it's very comfortable, because now you really have a probabilistic interpretation at the end, but the price of all this is that you need to accept the prior. Okay, so just to continue with the same hammer and the same nail, just a few extracts from a very illuminating article that I strongly recommend. So the frequencies consider that the probability is a measure of a frequency of potentially repeated events, whereas the Bayesians consider it as a degree of certainty. And roughly speaking, the frequencies consider the model parameters like theta to be fixed, simply unknown, and the data to be random, and you can generate new data if you want. On the principle, you may be able to do it. Whereas the Bayesians consider the model parameters to be random and the data to be fixed, simply because you have already your data. What are you going to do with it? Still another way to say it, the Bayesian would say, given the observed data, there is a 95% probability that the true value of theta falls in the credible region, whereas the frequencies would say there is a 95% probability that when I compute a confidence interval from data of this sort, so when I repeat that procedure, when I perform this procedure, the true value of theta fall within the confidence interval. And a posteriori, this means the frequencies saying, given this observed data, the true value of theta either is in the confidence interval or it's not in the confidence interval, which is perfectly indisputable. So who wins in the end? So like I just said, the frequentist approach is indisputable in the sense that whatever, you don't need to do any assumption. Whatever the true value of theta, they're right in saying that their procedure will say something true with a probability 95%. As a side note, if theta happens to be random in the real life, in fact, they are also right because just by linearity of linear combination of the probabilities. On the contrary, the Bayesians may be wrong if the prior is wrong. And personally, I think that it's for this reason that essentially frequentists have won. If you have a look at the standard practice in the scientific literature, you are supposed to use frequentist statistics. And I think that mainly because it's indisputable. The problem is that for your particular data, frequentism tells you essentially nothing, whereas Bayesianism will give you some information.
For instance, in Monte Carlo approaches, like you said, it makes sense because you're doing drawdown of random variables. So
no, the problem is that when you do a Monte Carlo approach on something, and that will be my very last example of the talk.
Well, theta exists and it's fixed.
Theta exists, it is fixed.
Yeah.
If you do one experiment, you do just one experiment. If you do 10 experiments, it's just a longer experiment. Yeah. So the confidence level that you can have in this big experiment is greater than in each of the small experiments. But at the end, still, theta either is in the confidence interval or it is not.
Sum up, basically, the frequentist approach is you're making an educated guess and you're trying to quantify how educated your guess is, but it's still a guess.
It's almost a guess.
No, it's not so much a guess because you define a procedure.
Yeah, your procedure is the way you guess. in
If
an
you want,
educated
yes,
fashion.
yes, yes.
As you said, we're evaluating how good the procedure is to guess correctly, but in the end, it's still a
Yes,
guess.
yes, yes, yes. But in the end, you cannot say how good your guess is.
No,
You can
it's a guess.
you can say no. You can say how good your guessing procedure is.
How educated the guess is.
Okay, so let's go for a Monte Carlo example. So this is the main example of the talk, and so be very focused while I present it because otherwise it's going to be really boring in the next half an hour. So we have a uniform distribution on an interval of size 1. Okay, so we know the size of the support, we know the variance. What we don't know is the mean, so we don't know the center of the interval. So it's a very, very basic case where you want to estimate the mean of a distribution. To simplify the example, I will assume that we have a sample of size 2. Okay, we have x1 and x2, and we want to estimate theta. Of course, it's difficult to have a very good confidence interval with only 2 values, so I will be modest and I will ask for a 50% confidence interval. Okay. So we will often need to refer to the minimum, which I will denote little m, and the maximum, which I will denote big M, which are, of course, random variables themselves, depending on x1 and x2. So we are going to start with a common sense approach. So as a general tip in math and elsewhere, it's really a good idea to start by simple things, just common sense. It will serve as a sanity check for later. So do you have an idea now for a 100% confidence interval on theta? Except, of course, R, blah, blah, blah. But given the data.
-1, max +1.
Max,
Max
yeah,
minus
be over.
1.5.
Max minus 1, yeah.
Okay, so that
Basically.
that's more like it. Okay.
Or if we can do.
So the distribution is uniform on theta minus 1/2 and theta plus 1/2.
Yes, max -1/2.
Okay.
Min +1.
Thank you. You're not asleep. So that's the confidence interval that I will denote A for all possible values, which is big M minus 1/2 and little m plus 1/2. Still warming up. Assume that I run an experiment and I found that little m is equal to something very close to 0 and big M is something very close to 1/2. So we have just noticed that we are sure that theta is in the interval minus something very small and plus something that is slightly greater than 1/2. What would be the probability that theta is between little m and big M? Ideas, remark, questions?
Because for instance, you've got the case where in both M and N, you draw above the average, in which case it would be below. So
The probability of it not being in that interval is if either the minimum is really close to the minimal bound, which is like 1% chance.
Yeah, I would be like one half. I don't know why, but
I give it like 99%.
Okay, so I have 1/2, I have
99.
99%, yeah,
99,
something close
yeah.
to 1. Okay. Okay, so the probability is 0% because theta happens to be equal to 0.00001, and I simply didn't tell you. The word didn't tell you. Or in fact, it is 100% because theta was equal to 0.35, and the word did not tell you. That's the frequentist interpretation. There's no probability, in fact. Theta is somewhere, either it's in the interval or it's not. That's perfectly normal frequentist interpretation. Okay, so now we will construct, so in fact, this is a very stupid 50% confidence interval, but we might see it as a simplified version of the true example that I will show you later. And so it may be a bit simpler to understand, and it already contains some key ingredients of the true example. So let's define B to be a random bit, defined by 1 if x1 is smaller and 0 if x2 is smaller. So it's essentially a random coin because x1 are drawn with the same distribution. The probability that x1 is equal to x2 is 0. So we have really one chance out of 2 that B is equal to 1 or to 0. It is also independent of my little m and big M, because okay, everything is symmetric. So knowing little m and big M, they can be x1, x2, or x2, x1 with equal probabilities. So now let us define SCI for stupid confidence interval in the following way. If B happens to be 0, then we'll take for SCI the 100% confidence interval, which is big M minus 1/2 and small m plus 1/2. Otherwise, we will define SCI to be something that is essentially useless. So if you prefer, you can take just the value of the mean, or you can take 4242. Or even if you consider that the DMT set is a valid interval because it's, for example, -1 minus 1, then you can take the empty set. So I pretend that SCI is a 50 confidence interval. Would you be able to prove that?
yes.
How would you do it?
For any experiment, the probability that B equals 0 is 1/2. In which case you return the full interval A, which contains theta.
Yeah. Yeah, the probability that the interval contains theta is exactly the probability that B is equal to 0, which is 1/2. Do you see? Sorry, yes.
Quick question. We said we don't know anything about the distribution. We do assume we know independence.
Yes, yes. We assume independence. Yes. So now, are you disturbed by this confidence interval? If not, I worry about you.
I don't see the problem here.
Okay, so of course, it's very disturbing because it really shows that a posteriori you shouldn't interpret gamma as a level of confidence in what you've learned. Because in this particular case, if the procedure returns an interval of positive length, you know that you are in the first case, and you know that the interval with 100% certainty contains theta. And in the other case, or in the extreme case, so you can assume even that SCI is empty, you know, of course, that theta isn't in the confidence interval.
So you know that you have 0 information on theta.
Exactly. In the second case, yes, but in the first one, by the way,
Yes.
the confidence interval tells you something.
Yeah.
Okay, so just repeating what I've already said. If I repeat the procedure several times, sometimes B will be equal to 1, sometimes B will be equal to 1. And on the long run, 50% of the times, the confidence interval will contain the true value. Before applying the procedure, as we noticed, I can say that the probability that the confidence interval will contain theta is equal to 50%. However, after applying the procedure, not only I cannot say that the probability is 50%, but in general, I can say that it's 0% of or 100%. So what is specific to this example that we don't see in general in real life about confidence interval is that here we know, we see the problem because it's especially obvious, but it's general in the sense that the confidence level cannot be interpreted as a probability a posteriori. Okay, let's try to construct another stupid 50% interval. And once again, it's to see if you are asleep or not. So now let's be a random bit that is defined a bit differently. It's the first fractional bit of x1. Okay, so you write x1 in a binary notation, and you have a look at the first digit, the first bit after the comma. And then similarly to before, you define the second stupid confidence interval, maybe, by A if B is equal to 0, and by, let's say, empty set otherwise. So first question, is B a fair coin flip?
Not necessarily.
Yes.
Sorry?
Yes.
Yes. So no, yes.
Depends on the support. If the support of the distribution is only on the first half of 0,1, for instance.
Okay, so just as a reminder, the support of the distribution is between theta minus 1/2 and theta plus 1/2.
Okay, so
Unit interval.
okay, so maybe it's yes in that case.
So it is a fair coin flip, yes.
Yeah. Sorry, I forgot that it was.
Yeah, no problem. No, it's also why questions are important is because it allows to see what assumptions were forgotten in the course of the talk. Is B independent of M and M? So no.
Depends on theta.
Depends on theta, but not in general.
I think whatever theta is, it's whatever theta, it's not independent. But just as an example, if we happen to have M and M in 0,1/2, then we know for sure that B is equal to 0. So it's not independent. And the last question, is SCI prime a 50% confidence interval?
If B is fair, yes.
I have yes here. Two yes. Still no for the moment. Okay, yes, it works the same way. It's exactly for the same reasons. So it was just to mention, also to challenge you, and to mention that the independence of B and MM was comfortable in the first exam, but actually not necessary for the argument. Okay, so now let's go with the real confidence interval. So essentially, the problems will be the same. It will be slightly more technical, not that much. But I really think that the stupid confidence interval that we've seen captures the key ideas that we are going to see now. Okay, so first I will define it by saying that if the difference between the two m's is big enough, then I will take all the possible values, m minus 1, m plus 1, m minus 1/2, and small m plus 1/2. Oh, I have a message in the chat. I don't get how B can be a fair flip coin and at the same time be 0 with certainty sometimes. Okay. It can be 0 with certainty conditionally on small m and big M.
The experiment.
Yes. So if big M and small m are far enough, then I will take A to be all the possible values. And if M and big M and small m are close enough, then I will simply take the interval between them. Another way of writing this to say that my interval is between the max of big M minus 1/2 and little m and the minimum of little m plus 1/2 and big M. So it's not necessarily obvious that it's a 50% confidence interval. So we are going to start by checking that it is indeed a 50% confidence
By the
interval.
way, I would have thought that just taking little m, big M would be a 50% confidence interval.
In general,
Yeah.
uh,
With your example, with uniform distribution, with a uniform distribution.
we can check, I think. But I think that it's not the case.
There's a probability that one of the value is above and one is below.
Yes, as a matter of fact, it's correct. Yes, it's correct.
Right.
Yes, it's correct.
Okay.
Yeah.
This just makes it more precise than that further values apart.
Maybe. Yeah. Mm. Yeah. Yeah. Mm.
Yes. Yes. Okay. So let's go. Oh, another message. Okay, thanks. Great. Okay, so as a reminder, the form of the confidence interval. So here, even if I don't know theta, I can do a plot with the value of theta and what happens around theta. Okay, so little m can be between theta minus 1/2 and theta plus 1/2. Big M can also be between theta minus 1/2 and theta plus 1/2. There's a forbidden region here in gray because we know that big M is greater than small m. And there's an interesting limit here, which is whether big M minus small m is greater or lower than 1/2. In the first region, the confidence interval is big M minus 1/2, little m plus 1/2. So is it the case that theta is here? So to say it otherwise, is it the case that little m, for example, is greater than theta minus 1/2? Yes, of course. And by the way, is it the case that m is greater than theta plus 1/2? Smaller than theta plus 1/2? Of course, it's the case. Of course, because anyway, this interval is the 100% confidence interval. So we know anyway that for big M minus small m greater than 1/2, we are sure that everything will work. And this is what I represented here in purple, the fact that theta is in the confidence interval if the pair small m, big M happens to be in that region.
Actually, we see here that the condition
Yes.
small m is the square. Not the,
yes, exactly. In the other case, so where big M minus small m is smaller than 1/2, so it's in the confidence interval if small m is smaller than theta. So I'm here not small m here. So small m here. So small m should be on that side here on that here somewhere here. And big M should be greater than theta, so big M should be here. So that is why we have the square here. Another way to see it is with Fabien's formulation. Okay, so now the area of each of the zones represent its probability. Okay, so of course here we have 1, 2, 3, 4 similar triangles, and it works in 2 triangles out of 4. So it's 50%. It works with 50% confidence.
What we're saying compared to what we were saying.
Sorry?
Now, here, whether we always take the interval small m and big M, or we also take the left interval in certain cases, we still have only 50% confidence interval.
Yes.
However, when we take the left interval, we just have a smaller interval.
Yes, exactly.
But
Exactly.
it's still
Exactly.
the same confidence.
Do you have
Exactly.
relation where you add the range of the provided interval to the probability that is given, or
Sorry?
do you have performance metrics where you try to mix the size of the interval given the probability that it contains theta? Or is it-
Okay, so in fact, it's even worse than that, not worse, but more than that, that amongst the 50% interval, you can define one that is optimal in some sense, in the sense that it's the smallest possible for a good sense of smallest. Okay, and that's one of the things that we are going to illustrate in the rest of the talk. So excellent transition for my next slide. In fact, it can be shown that here CI is optimal in a complicated sense. It's smallest in a complicated sense. So we will not prove that, and I would not be able to do it. But we will at least we will illustrate that it's smaller, for a good sense of smaller, than another confidence interval that I will show you. So here, this confidence interval has surprising properties that are similar to my stupid confidence interval. In fact, when m minus m is greater than 1/2, then CI is guaranteed to contain the true value theta, and you know it because you see that big M minus small m is greater than 1/2. On the other extreme case, when big M minus small m is just very, very small, then you may know that we have very little information because all the possible values are on an interval of size 1. But the confidence interval will tell you, okay, it's between small m and big M, which is a very, very small interval that excludes almost all the possible values. And we can, just to continue on that and to illustrate what I've just said, we can have a look at the probability that theta contains the confidence, is in the confidence interval, knowing the difference between small m and big M. So all the events with a constant, with a given value of big M minus small m are on the blue line here. When it's in the purple region, then theta is in CI, and when it's in the white region, then theta is not in CI. So when the difference between big M and minus m is very small, in fact, there is a wide range of possibility, but with very small probability, you will have theta in the confidence interval. And as soon as big M minus small m is greater than 1/2, you are sure that it's in the confidence interval. And all these averages out to ensure that the global probability is 1/2, but that's the only thing that the procedure guarantees to you. And thank you, Fabien, for the talk on IPyWedget.
I saw that.
So now let's have a look at the Bayesian approach, the credible region. So I'm going to check once again if you are asleep. So we know that theta is in the interval that I denoted A, which is the set of all the possible values given small m and big M. This interval can also be rewritten like this. It's an interval that is centered on the empirical mean, which is the average of big M and small m, and the width of the interval is 1 minus m minus m. would you have any idea for a 15% credible region?
Should be the prior. First.
Okay, sorry. Yeah, excellent question. So let's say that, and I will take big quotes here, that the prior is a uniform probability on big R. Okay. Sorry.
Big R.
Hey, that's why that's what I take the quotes. But let's say that now that you know with certainty that theta is a big A, let's say that you have a new prior that has magically appeared that is uniform on big A.
So you take anything that is 50% of this interval.
Okay, anything that is 50% the length of this interval. Yes, exactly. So the most natural choice is to take an interval that is centered on the mean and that has half the length of the original interval. But as Fabien mentioned, you can actually take any interval that is contained in A and that is half as big, half as large, because it will capture half of the probability. Yes.
I don't see why the prior's knowledge would be maybe it's the case.
Where is the trick here?
It's normal. It's an assumption.
No, because
So when you take the prior, it's always an assumption. So you can do a more or less natural assumption, but it's always an assumption. That's the main weakness of the Bayesian approach.
I think there are some possibilities to compare different priors and try to find what is the most probable. I do not remember how to do that.
So
it's possible to do
I think I see where you're going. So one of the things that you can do, for example, is to take a prior with maximum entropy.
Yeah,
That's I think I read in your mind. So
I did not have the word.
So
maybe I don't know, but if you try to do this on this problem, what would be the?
It would be uniform.
It would be uniform.
Yes. Yes.
I do not,
So, but
I don't remember how to do that.
But even saying that you want to take the prior with maximum entropy itself is a kind of position of principle. Yeah, it's difficult to ground this in something.
Will you propose some auto prior techniques after? Or?
No.
No. Okay.
Not in this talk.
Okay.
Okay. So it happens to be the case that in this example, the credible region is also a 50% confidence interval. Okay, pass this sentence in your head. So we defined CR as a natural 50% credible region in the Bayesian sense. But in fact, we will see that it happens to be a 50% confidence interval.
Yeah, that was my question.
Yeah, that's of course.
That's optimal.
Yes, that's really what we will illustrate. Okay, so here, so the credible region is defined like this. So if you want to see, for example, if theta is in here, it means, for example, that this is smaller than theta. So this is a linear equation defining a line, and you see more or less that you will have something like 3 big M and 1 little m, or the opposite, which makes lines with the slopes of 1/3 of slopes of 3. And that's why you end up with these two lines of slope -1/3 and -3, delimiting the zone of the pair MM such that the credible region contains the true value of theta. And as you can see here, it's the point theta -1/4 and theta +1/4. So here this line is divided in 4 equal parts. And so these two triangles, the white triangle, they have the same height as the purple triangle. So these two white triangles have the same area as the purple triangle. So there's a 50% probability in the frequency sense that this interval contains the true value of theta. So here it's a bit more intuitive because when little m and big M are far, then so when do we have good information of theta when little m and big M are far? Yes, very good, because if there are distance ones, then we really pinpoint the value of theta. It's the average. Then big A is of length 0 because there are very few possibilities, and the credible region is also of length close to 0. On the opposite, if the two values happens to be close, then we have little information on theta because it can be as far away as little m plus 1/2 and as far away as big M minus 1/2. Then A is of length close to 1, and in fact CR is of length close to 1/2. So essentially, the more information we have, the smaller the credible region, which is quite moral. And once again, we can see this by computing the probability that, and here it should be CR, not CI, the probability that it's in the credible region. So once again, it's the part of the line that is inside the purple region. And in fact, it's always 1/2. So you can really say that the probability that theta is in the credible region is equal to 1/2. Yes?
For me, this is something I was expecting for an interval.
For confidence interval?
Confidence interval to not depend too much on the data.
But that's not in the job description of the confidence interval.
This is what I would have expected.
Yeah, but that's precisely the reason of my thought. Okay. So now, what is the probability that a given incorrect value is in the interval? That's also a measure of quality. We know that the probability that the interval contains theta is 50%. Okay. Now let's take another value, theta1, that I will also denote sometime by theta plus delta, a value that may be different from theta. Of course, we would like the probability that the confidence interval contains theta1. We want it to be small. We want the probability that the interval contains theta, we want it to be big. But for a value that is different for theta, ideally, we would like it to be small. So we can compute it. I skip the computation. It's not really complicated. So theta is in the confidence interval if blah, blah, blah. So this corresponds to a square in my MM diagram. And simply this square moves when the value of theta1 is moving. So
the square is a rectangle.
My square is a square. It's just that sometimes it is out of the possible bounds.
So it's a rectangle.
Yes, but just to capture the plot mentally, I think it's good to think that it's a square that you cut. Okay. Because then you will really see what's happening. Yeah. What's happening. So here you have theta1 and theta1 minus 1/2. And for the big M part, you have theta1 and theta1 plus 1/2. Okay. And so when, of course, when theta is very far away from theta1 is very far away from theta, this probability diminished, which is morally satisfying. And in fact, it diminishes quite quickly. And I will say why, in what sense I say quickly. And for the credible region, so you can also solve the equation, and it will be a bit similar in the sense that now your big triangle here is moving with the value of theta. So of course, when the difference between theta and theta1 is 0, we find again the diagram of before. And when theta1 is different from theta, the triangle moves, and a part of the probability disappears by the cut. And algebraically, what we can see is that for the confidence interval, the probability that this wrong value θ1 is captured by the confidence interval decrease linearly with delta, whereas for the credible region, in fact, it decreases only quadratically, in fact, in delta. And finally, if we compare the two, so here it's the plot where on the x-axis, I have delta, so the difference between theta and θ1. And on the y-axis, I have the probability that this incorrect value is captured by the confidence interval or by the credible region. So here for the confidence interval, as I told, it decreases linearly with delta until delta is equal to 1/2. And for the credible region, it decreases quadratically until delta is equal to 3/4, in fact. So this means, so it's very impressive, because whatever the incorrect, whatever theta, so for any value, true hidden value of the parameter theta, and for any incorrect value θ1, the probability that θ1 is captured by the confidence interval is smaller than the probability that is captured by the credible region in this example. And in fact, it is in that sense that this confidence interval is optimal. So we have only illustrated the fact that it's better than CR from the point of view of the theory of confidence interval. Okay, so I'm more or less on time. Conclusion, just to see how many people did fall asleep during the talk, I have a final quiz. So I want to do a Monte Carlo estimation of phi. So it's a very famous example of the Monte Carlo method. I will draw some random points on the plane with x between 0 and 1, y between 0 and y. Everything is uniform, everything is independent. And for each point, I will record if it's a blue point inside the unit circle, or if it's an orange point outside of the unit circle. And at the end, I say that in theory, on the long term, the proportion of blue points should be p/4. So to estimate p, I will just take the proportion and multiply it by 4. So believe me, I ran the experiment and I found that, sorry?
How many times?
0 times because I am lying. And empirically found that I had 7,980 blue points out of 10,000. So I used my favorite confidence interval algorithm and deduced that P is, yes, P, the probability of a point being blue, is between 0.788 and 0.808 with 95% confidence. From this, I deduce that pi is between 3.152 and 3.224 with 95% confidence. So what is the probability that pi is in the confidence interval? It's 0. Thank you very much, because p is equal to 3.14 and something. Okay, so as I said many times, the main takeaway of this talk is that you should not interpret confidence interval, confidence levels and confidence interval as probabilities a posteriori. That's not a level of belief that you can put in the end result that you have. It's only a probability on the procedure that you apply before applying it. Some references. So general, the Wikipedia article on confidence interval and credible intervals are nice. I really love this article, which gives another example of trap with the confidence interval with the truncated exponential distribution. And about the main example of the talk, so the simplified version of the argument is in the Wikipedia article on the confidence interval. The original version of the argument is in this book. And to be honest, I didn't open the book, but I opened this book review where the argument is also a bit explained. And thank you very much for your attention.